right, so this is the second time I've tried to record this, so hopefully this one goes a little better. Today we are starting section 4.4. It is the classification of rigid motions. So we're going to take a look at some figures and talk about symmetry. So our learning target is I can determine if a figure has reflectional or rotational symmetry. So let's start by talking about what the two types of symmetry are. We have reflectional symmetry and rotational symmetry. So reflectional and rotational, these are words that we've used already. These are both rigid motions. So reflectional symmetry is symmetry which a reflection can map the figure onto itself. Okay, so what that means is if I was to have a figure here, I'll draw a trapezoid. Okay, is there a line that I could draw in here so that we cut it in half and this side would reflect over the line and match up with this side and this one would match here? You guys have learned this probably like fourth grade range where you talk about a butterfly and the butterfly's wings close up and it matches up perfectly because it has reflectional symmetry. Or somebody's face typically has reflectional symmetry because one side matches exactly the other side. This is also known as line symmetry. Okay, because we can draw a line. Now, some figures are going to have lots of different lines of reflectional symmetry. This one only has one. If I was to try and reflect it over this line here, would this point match up with an exact point on this side? No. So this line does not exist for symmetry. Now, rotational symmetry is symmetry for which a rotation can map the figure onto itself. And then I'm going to say in less than 180 degrees. So that's one of the stipulations. So now we're talking about a rotation. Can we turn something and have it fit in the same thing? So this is more of a puzzle piece. Most puzzle pieces don't have rotational symmetry, but if I had a puzzle piece that looked like that and I'm working with my puzzle, I can put the puzzle piece in this place two ways. I can set it straight here, or I could rotate it 180 degrees and it will still fit in that same spot. Could I rotate it only 90 degrees and have that piece fit into it? No. So this figure right here, this rectangle, has 180 degree rotational symmetry. We're going to take a look at that right here. So example 1, what transformations can be used to map the figure onto itself? Why can some figures be mapped onto itself? So it has symmetry if a rigid motion can map the figure onto itself. So does this have reflectional symmetry? Is there a line in this weird looking star that I can draw and have it match up? Yes, they already did it. We have this line M. It'll fold along that line. However, that's not the only one. We can also fold it here. So yes, it has two lines of reflectional symmetry. It has, two lines here. Now, could I fold it right here? No, because this is not a square looking figure, because each of these sides are not the same length, I can't fold on a diagonal. So a lot of students struggle with this. They think that things that are rectangular shape can fold along a diagonal, but I'm going to show you if I back this up and match up these corners, do you see how that doesn't match up perfectly like it would if I was to fold it here or fold it here? So when it has a longer shape, it's not going to have reflectional symmetry along a diagonal. Now, is there a way I can turn this? If I had a puzzle piece that looked just like this, I could put it in this way. Okay, I'm going to follow that point. Or I could turn it 180 degrees so that that point is actually over there and it would still fit. So yes, this also has rotational symmetry. So now we're going to take a look at these figures. Rotational. Follow this little point right here. Is there another spot where I can turn this and that point would fit? Yes, right over here. This has rotational symmetry. Now, does it have reflectional symmetry? Yes, I could fold it right there. I could fold it right there. Could I do a diagonal here? No, because this is more of a longer shape. It's more of a rectangle. All right, so yes, it has reflectional symmetry. 2 lines. Rotational symmetry here. Well, let's just check some things. If I rotated it 90 degrees, is it the same figure? No. If I rotated it 180 degrees, is it the same figure? No. Once you check 180, you don't have to check anymore. So no, this does not have rotational symmetry. Now, is there a line that I can draw on this face and have everything match up? Yes. All right. Now this one is asking how many lines of symmetry does a regular hexagon have? First of all, regular means it's the typical shapes you guys see. It has congruent angles and congruent sides. In this formula, this recipe is usually causes there to be symmetry. Now a hexagon has 6 sides here. So is there a spot where I can fold it? Well, let's check the 2 most obvious ones. We have a vertical line that allows me to fold it. I could also fold it along this horizontal line. Now, students have a hard time seeing this, but you can go ahead and turn your paper so that now this piece is on top. Well, we could go a vertical line there, horizontal line there. You can keep turning so that you have the same figure. Now I'm going to give you a hint, okay? Regular figures, so figures, shapes that have the same size with the congruent angles, congruent sides, they're going to have the amount of symmetry lines as the amount of sides. So since this is a regular hexagon, I know without doing anything, it's going to have 1, 2, 3, 4, 5, 6. So make sure when you count these, you only count each line once. Some students try and go around and tell me that this has, oops, that shouldn't be there, 12. But if you count this, you're actually counting this line up here that you already drew. So 6 lines of symmetry. Now, will that trick work here? Well, think about it. Is this considered a regular quadrilateral, a 4-sided figure? We already know that it fits here and here. Well, since this side is not congruent to this side, we're not going to have 4. We're not going to have the diagonals. So this only has 2. Now this one over here is not a regular figure. It's a trapezoid. It does have 1 line of reflectional symmetry though. It'll fold, that will match with that will match with that, but it does not fold across. All right. All right, so what angles of rotation does the figure map onto itself? We're not going to worry about the angles right now, but I'm going to draw an equilateral triangle. So we're working on rotational now. Equilateral triangle means all sides are congruent, so it's a regular triangle. So lines of symmetry, I should be able to come up with 3. But rotational symmetry, what they're asking about is, if I was to cut out a piece this way, how many different times will it fit in there? Okay, well, it'll fit in with this point at the top. So there's 1. I can turn it and it'll fit in here. There's another one. I can turn it so that point at the top is here. There's our 3rd. So this has 3. This can be fit 3 times. It does have rotational symmetry. Now, just for future reference, if you wanted to find the degree of rotation, you take the 360 degrees, a full turn, and divide it by number of times that the figure fits in there. So this has 120 degree rotational symmetry. Now a parallelogram looks like this. I'm bad at drawing these figures freehand. Now, be careful because we have 2 obtuse angles and 2 acute angles on this parallelogram. This obtuse angle is only going to fit over here. So there's only 2 different ways that we can put this puzzle piece in. So yes, it has rotational symmetry. Okay, the degree, since it fits in there twice, would be 180 degrees. I can turn it so it fits also 180. All right, what are the rotational symmetries for this? Can this be turned? Yes, this point will fit once, twice, 3 times, 4 times. So yes, this has rotational symmetry. If I wanted to find the degree, I take 360 and divide it by the 4 times that it'll fit, 90. This one here, there's no points to follow, but you can create a point. Okay, where else will this point fit? Can I turn it so it fits somewhere else? Yes, it will also fit over here. So it has rotational symmetry. The degree would be 180 degrees. This is considered, this is not an actual shape, but it has some of the qualities that we've talked about. Okay, this petal is congruent to this petal, this petal, this petal, and this petal. So this point right here, how many different spots will that point fit? It'll fit here, 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 and here. So there's 5 different ways that this puzzle piece will fit in there. So yes, it has rotational symmetry. The degree is going to be 360 divided by 5, 72 degrees. Now this card, oh wait, sorry, does this have reflectional symmetry? Yes, well since it follows the regular figure characteristics, it's going to have 5 lines of symmetry because there are 5 congruent parts there. Question here, these dots, I did not draw on there even though it looks like I did. These dots make it seem like you would think that you could fold this here and here, but pay attention to the dots. We have to look at every little detail of this. If I was to fold it along here and this flipped over, is there something for it to match up with? No. Could I fold it there? No, because that won't match up. So this does not have reflectional symmetry, but I can rotate this card so that this point ends up over here and the dots actually match up too. So this has rotational symmetry of 180 degrees. So one thing I want to point out, figures can have reflectional symmetry without rotational symmetry. We saw that with the smiley face on the other side. And they can also have rotational symmetry without having reflectional symmetry. In your assignment, you're only going to have to determine whether or not they have reflectional, rotational, or both. You won't have to do this degree thing. All right, so good luck, and sorry this video was a little late.